Yes, ma'am.
Okay. So, in today's session, we'll be covering two classification algorithms. So, which algorithms were covered in the previous session? I think it was. One second. Hello. Okay. I hope my screen is visible.
Yes, ma'am.
Okay. So today we'll cover two classification algorithms as mentioned. So the first algorithm would be decision tree, and then it would be KNN. So decision. So let's start with the implementation of decision tree. So before moving on to decision tree, the most important function, or like the most important thing which we should know is that it's about entropy. So entropy is going to accept the proportion of points which belong to class 1, and it is going to return its and it's going to return the value known as entropy. So it's helpful in measuring the impurity in the data set. So we'll be using this entropy function. So here, if p equal to 0 or 1, that is a proportion of points belonging to a particular class, then we'll return 0. If not, we'll perform this operation, that is p into here np.log2 stands for natural logarithm, and natural log of p minus 1 minus p into log of 1 minus p. So this is the formula for entropy. So as an example, if I take p as 200 by 1000, so p is like the proportion which is going to be between 0 and 1. The entropy of p is going to be 0.72. This is how we measure entropy. And since as I've already told, entropy the value of p is going to range between 0 and 1. That it is basically probability. So if I take an array which is going to have which is going to have equally spaced numbers, which is taken from the interval 0 to 1, we are taking 100 points. Like these 100 points are going to be like 1 by 100 is 0.01, so it would be 0.01, 0.02, 0.03, so on up to 1. So if I take all these points and put it in an array called p, and then I'm using a matplotlib to plot this x along with its entropy. So when I plot it, I observe this graph. This is like the proportion versus the entropy graph. Note that when the proportion, when that is when the value of p was very low, entropy was also low. But when the value of p is slightly increasing, the entropy also began to increase. But once at p equal to 0.5, you can observe that at p equal to 0.5, entropy is maximum. It's almost close to 1. And after that, it is again decreasing. So entropy is having this kind of behavior, that is it is that is it is moving towards a global maximum, and then it is beginning to increase. So our task will be to obtain the central portion where the entropy is maximum. We'll try to maximize it so that our classification algorithm performs really well. So let's begin to explore another term, like which is superior to entropy, that is information gain. So I'll explain this formula and whiteboard. So information gain makes use of entropy to calculate the total information which you gain after looking onto the classes and examples in a data set. So let's take the example of a data set which has 1,000 data points. So in this 1,000 data points, let's consider that 200 data points are classified correctly. For example, here there are 1,000 data points. In this 1,000 data points, 200 data points are classified correctly. Let's say there are two classes named uh, class 1 and class 2. uh, if I say that 200 data points are classified correctly, a part of the 200 data points points are going to be classified correctly as 1, and another part is going to be classified correctly as class 2. The rest of the 800 data points are not correctly classified. That is, if a point belongs to class 1, but the model predicts that it belongs to class 2. So the prediction is incorrect. So this is the example which we are taking. And then let's say that in class 1 we have a total number of data points as 100, and in class 2 we have 900. So class 1 we have 100, and class 2 we have 900. So this is the distribution of data points into these two classes. And so the correct now let's say from class 1, the data points which are correctly classified as class 1, that is correct classification, is going to be 50. 1 minute. Okay, let's say 50 data points from class 1 is correctly classified, and let's say 150 data points from, this is for class 1, 150 data points are classified correctly in class 2. So this is the information which we have now. So now let us consider two parameters. The first parameter is going to be for class 1, and the second parameter is going to be for class 2. So let me consider them as Q and R respectively. So Q is for class 1. So now we want the proportion of points belonging to class 1 which is correctly classified as class 1. So what would that proportion be? The total number of points in class 1 is 100, and total number of points in class 1 which is correctly classified as class 1 is 50. So what would that proportion be? Any idea? Any idea? So the proportion is going to be 50 by 100, correct? Right? Because 50 points which is belonging to class 1 is correctly classified as class 1, and the total number of data points in class 1 is 100. So this would be the value of Q, that is 50 by 100, which is going to be 0.5. And the next parameter is going to be for class 2, which is going to be R. So R is going to be number of points belonging to class 2 which is correctly classified as class 2, right? So here it is going to be 150 by 200. So the value of this would be 3 by 4. These two values are required for calculating information gain. So the formula for information gain is E minus gamma into EL minus 1 minus gamma into ER. So I'll explain each and every terms here. Here let us consider class 1 as left child and class 2 as right child. So if you consider like this, EL is going to be for left one, right? So EL would be EL is going to be entropy of Q, and ER is going to be entropy of R, and E is going to be entropy of P. And E is going to be entropy of P. P is the total number of data points which are correctly classified in both the classes, right? So this E is going to be 200 by 1000, because The total number of points which are correctly classified is 200. So 200 by 1000 gives you this value. So now finally what we are going to do is that we are going to take entropy for everything and then subtract it accordingly. So and gamma value is 100 by 1000. This is for the right side. So for right, it is going to be the total number of data points. I think it's this is for the left side. Okay, this is for the left side. So for the left side, this is going to be 100 by 1000. So I'll write everything. Am I audible? Sorry, like I lost the connection in between. So 1 minute. Okay, so the logic behind it, I think everyone would have understood. We are calculating P, Q, R, E, EL, and ER. E is going to be the entropy of the whole proportion which we are taking. That is total number of points which are classified correctly by the total number of points. And EL is going to be entropy of Q. Q is going to be number of points classified correctly as class 1 by number of points belonging to class 1. And for R, it's number of points correctly classified as class 2 by the total number of points in class 2. Then what we are doing is that we are doing information gain for E, EL, ER, and gamma. So I hope you have understood up to this part. So for the data which I gave, the information gain was around 0.036. Higher the information gain, higher is the probability of getting a very good classifier out of it. So let's see the next problem. So okay, I'll skip this part and we'll see how. So, before moving on to this, okay. So here, let us consider a decision sum which is going to have 1000 data points. Let us call a node Q as a root node, and there are two nodes. That is, if you consider a decision tree, there would be left side roots as well as right side roots. So the left side is going to be L. The nodes belonging to left side is L, and nodes belonging to right side is R. So the proportion of data points that belong to class plus 1 in Q is equal to zero point 0.4, and the proportion of points which is belonging to left node is equal to zero point 0.7. Here the gamma is 0.7. So and Q is going to be the proportion of data points that belong to the class plus 1 in L. So if you want to find Q minimum and Q maximum, let's say we are considering the data points with 1000, and here P is 0.4 as which is already mentioned, and gamma value is 0.7. Qmax and Qmin can be just consider found by minimizing and maximizing P by gamma. So that why we are doing P by gamma is that if there is any value greater than 1, we'll populate Qmax with it, else we'll just populate 1 with it. And in Qmin, sorry, this is for minimum. So if there is any value less than 1, we'll give P by gamma. If not, we'll give 1. And for Qmin, it's going to be max of 0 comma P plus gamma minus 1 by gamma. So this is the values for Qmin and Qmax which we obtained after doing this. Let's try plotting this and observe what's happening actually. So if I run the cell, I got a graph in which this is going to have q values and this is having information gain. So we can see that the orange line is q minimum. The q max isn't visible here, but the q max comes around here, that is 0. This graph is actually extended even beyond the line, so it's around 0.57. So now let's work with the data set and visualize how a decision tree actually performs. So here I am generating a data set and then running this array, and I'm just having two classes, that is left class and right class. Here it is going to be red and green. If I visualize it, this is how my like visualization should look like. This is the actual data set, that is the green points are belonging to class 1 and red points are belonging to class 2. This we just visualize the data set. Now let's try fitting a decision tree classifier into it and observe how it performs. So let's see how decision tree works. So basically for decision tree, I've written two functions. One is best split and the other one is growth tree. So this algorithm is bit complex, not very complex, but if you understand the overview of how it's happening, it's actually sufficient for this course. So this algorithm is named as best split because it's going to find the best split, which is going to divide both classes such that there is no overfitting or underfitting. So what I'm doing is that first I'm taking the minimum values and maximum values from the data set and populating it into the variables. Then I'm generating values between minimum val and maximum val. That is 10 values between min val and max val. And after that, I'm actually finding the proportion of points which belong to class 1. Here we are not checking whether the point is correctly classified or not. We are just checking if the point belongs to class 1 or class 2. So P is going to be like x of y equal to 1. In NumPy, you can do x of y equal to 1. This generally means that the data point is having a label of 1, and then I'm obtaining the shape of it, that is shape of 0. This just says that how many data points are belonging to class 1, and we are dividing it by the total number of data points. After doing this, I'm finding the entropy of P. As we already saw, we'll be finding entropy of both the left child as well as the right child for the information gain. Now to find the best information gain value for the following decision tree, I'm initializing all the values to 0. Now I'm iterating over vals, and for each feature in 0 comma 1, here we are here we are basically having two features. We are like, this is a two-dimensional graph. So we are having two features, this is x-axis and y-axis. For each feature in 0 comma 1, we are actually having we are doing this left child and right child. If we are checking whether the value of y is less than val, that is y of x up to features, that is we are checking up to in the first iteration it would be checking only the first point. In second iteration it will be checking for the first 2 points, and this will continue. And then we are checking for the right also. Here we are finding the value of gamma by finding the number of points in left child by the total number of points in x. After doing this, we are checking whether the left is having a value. If it is not equal to 0, then we'll update q, because we want the value of q and r for information gain. We'll update the value of q and r accordingly. This is just finding what is left of left equal to 1 is checking is that if a point belongs to left class, that is if the point belongs to class 1, and if it is accurately predicted as class 1 by the model, then this prediction is accurate, right? So we'll find a proportion of the of the classes in which the data points are correctly classified as that particular class. So we are basically finding that proportion here. This is for the left class. In the previous example, we took, I think, 50 by 100. That is 50 points belonging to class 1 were correctly classified as class 1, and the total number of points were 100. Similarly, this is done for left, and this is done for the right subtree. And after this, we are actually finding the entropy for the left and the right, and then finally finding the information gain with the formula. And then we are updating the best information gain value and the best value and the best feature value and returning them finally. So the value which we obtained is feature best is 0. Here it is 2.06, and then the information gain is 0.3112. So now let's grow the tree and check. So this is just doing if the entropy is less than 0.2, we'll again do this proportion. That is, if the point belongs to class 1 and it's actually classified as class 1, and then we are updating the state and the leaf with the label. So this can be better understood when I show the scikit version of this. So here everything is coded manually, but in practice you needn't do this. So now this is a small code which I wrote for prediction. That is, given a point and given the model, um, whether the point belongs to class 1 or class 2. In this case it's green or red. So it's just predicting. If the feature is less than val, then we are updating index and doing calling the predict function. And after that, when I plotted the decision boundary for the graph which was above, the decision boundary which was obtained from my decision tree model was shown like this. That is, this portion, this portion, this portion represents the green points, and this portion represents the red points. So let's see the above graph. So this was initially the data set which was given to us. So we can see that this region, say, one second, I'll show. Uh,
Just control V.
next page.
Next page line கிடையாது. இது தொடு. கீழே போ.
So this is the data set, and we can see that the kept for testing, and the rest 80 is kept for training. So after this, we are running the decision tree classifier, and when I run the decision tree classifier, this is the visualization of decision tree. That is, basically in Iris we have three prediction, four features. One is petal length, petal width, sepal length, and sepal width. And after that, we have to predict whether it belongs to four classes. I think it has four classes. Let's see. This is white train. So um, set of y. Okay, so this is having three classes. The three classes are 0, 1, and 2. 0, 1, and 2. We have to predict whether the particular iris flower belongs to class 0 or class 1 or class 2. So this is how now we are calling the decision tree classifier by just using decision tree classifier, and then I'm fitting it with the training data and the X train and Y train, and I'm plotting the predictions for the training data by using the plot tree feature available in Scikit-learn. So here I'm giving field equal to true so that we can see all these values, and feature names is data dot feature names. So data dot feature names is, as I
Ma'am,
already mentioned.
screen not visible, ma'am.
Oh, okay. Thank you for saying. Uh, 1 second. Is it visible now?
Yes, ma'am.
Yeah. So I'll brush through the scikit-learn once again in a small way. So this is what I was explaining. That is, we are importing the data set from sklearn, and we are doing everything by using modules instead of coding. So we are just calling the functions which are already predefined in scikit-learn. So here we are dividing the data set into two parts. That is train data set and test data set. That is, if the data set is of size 1000 or 100, then in 120 data points are allocated for testing, and the rest 80 data points are allocated for training. So here we are mentioning a random state of 42, so that when you run the cell again and again, no new data points would be gathered in train or test. That is, for example, if there are 100 data points, it is randomly taking 80 data points and allocating it for train, and another 20 random allocation is done for y. Is done for testing. But if you mention the state 42, when you run the cell again and again, the same random points are going to go to train and testing. Here I'm using the decision tree classifier, and I'm fitting it with the X train and Y train. And after fitting it, I'm plotting a tree with filled equal to true. That is, the values are going to be filled here. And I'm using the feature names. Class names is data dot target names, and rounded is true. So this is the visualization. This is how a decision tree looks. So here this is the left class. Here in left side you are having only one leaf node, and in right side you are having many leaf nodes. That is 1 2 3 4 5 6 sorry, 1 2 3 4 5 6 7. There are 7 leaf nodes in the right subtree. So this is how a decision tree looks like. And then you can see that is here petal length is less than or equal to 4.95. This is how a decision tree actually classifies. That is, if you take a set of data points, it will give tight boundaries, and make sure that the points are correctly classified into either class 1 or class 2. Here the tight boundary which is specified is less than or equal to 4.95. If it is less than or equal to 4.95, then it goes to the right subtree, else it goes to the left subtree. That's how the classification is done in decision tree using scikit-learn. So let's move on to KNN. KNN, more than an algorithm, it's just like this algorithm is the most easiest algorithm in machine learning, at least for me. So how KNN works is that it's like, so basically, KNN is doing a majority ranking. There is nothing more in KNN. So if I take, uh, okay. So for example, if I have if I have five data points, say P1. If I have five data points, say P1, P2, P3, P4, and P5. and I have a 6 data points, say P6. Okay, so let's say the distance between P1, P2, P3, P4, P5. That's what I'm going to mention over here. It's going to be 5, 4, 6, 3, and 2. Okay, and let me specify the classes of point 1, point 2, point 3. There are basically two classes as of my this example. Let's say the two classes are going to be this is going to be green, this is going to be green, and this is going to be red, this is going to be red, and this is going to be red. So what KNN does is, in simple words, so it will arrange these data points in the order of their distances between the unknown data points. So by the way, this is an unknown data point which should be classified into either green or red. Okay, so this classification is done based on the distances between the other points. So let me arrange this in ascending order. So first we'll get P5, then we'll get P4, then we'll get P1. Sorry, it's P2, P1, P3, right? For P5 it is 2, for P4 it is 3, then for P2 it is 4, then for P1 it is 5, and for P3 it is 6, right? So now what we'll do is that if we have a parameter known as K, which is going to specify how this classification algorithm is going to work. Let's say if the value of K is going to be 3, then we'll consider the first 3 data points. Okay, by the way, let me put the colors also so that it will be easy to predict. So these are the colors of the points, that is, these are the labels of the points which I've colored in the bottom. So if K value is going to be 3, then it will check the first 3 data points. So what is the majority color? What color? Okay, what label is the majority of the points belonging to? We can see that it is going to be red. So this point P6 is going to be classified as red. So this is how the algorithm works. If I consider K equal to 2, then I'll consider the first 2 data points. But now it becomes like bit difficult to classify, that is whether to green or red. In this situations, we can use tiebreakers. So, but if we take the value of K to be 1, then it will check only the first data point. That is, the first data point is going to be P5, and P5 is green. So the classification would be green. This is how KNN works. So let's try coding this manually and then by using scikit-learn. This is very easy algorithm. It's very easy to code as well as to implement. But the only drawback in KNN is that it takes a lot of time, and it's not actually learning anything. It's just checking. It's like doing a nearest neighbor computation by checking only the data points near to it. And so let's see how KNN works. I'm creating a data point which has green points and red points. This is a random data point creation which is being done. I'm taking data points from a uniform distribution which is distributed uniformly between -10 and 10, and the shape is going to be 100 cross 2. Fine. Now I'm using the predict. So this is the predict function which is accepting 4 parameters, namely feature matrix, label vector, xs, and number of neighbors. So the distance between each and every point is computed here. That is what which is going to help the KNN algorithm to classify a point which is belonging to class 1 or class 2. So here I'm finding the distance. For distance, I'm using norm, and I'm actually subtracting x minus x. This should be reshaped so that both the data points are in the same shape. And then I'm sorting the list to sorting the list, and then I'm using arg here. So what arg sort does is that it doesn't give the points, but it gives the indices of the point which are going to be used for the classification. Wherever you use the word r, we are basically getting the index out of it. So now here we are summing the voters. That is basically it's like an election. The person who gets the maximum number of votes is going to be the CM or PM. That's how KNN works. The class like the class which is majorly used by the data points, that is the class which is belonged by major number of data points, is going to be the predicate class for the next data point which you are coming up. It works in the principle of CM or PM election, so you can remember this so you won't forget how KNN works. So if whichever voter is whichever candidate gets the maximum number of votes, uh, that candidate, the label of that candidate is going to go for the new data point. That's how it's being done. And I'm taking a random data point and okay, so one second. So when I took a random data point minus 3 comma 2, the prediction for the random data point is green based on the KNN. So now let's observe how the boundary of KNN was for different values of K. So whenever you are reducing the value of K, the model is going to be overfitted. That is, it's going to consider the outliers too. So this is for K equal to 1. As you can see, this is a very tight boundary. And in K equal to 2, the boundary is bit reduced. In K, so this is K equal to 3. And in K equal to 7, still the boundary is same. In K equal to 15, the boundary is same. But in K equal to 31, there is a better classification. That is, we don't need our model to get overfitted. Here, and at K equal to 63, it performs like this. That is, underfitting occurs. So when K value reduces, it becomes overfitting. And when you increase the K value, it becomes underfitting. So now let's see the final KNN implementation using Scikit-learn. So here same thing which was done for decision tree is done. I'm splitting the data set into train and test and then running the K nearest classifier with the n value, that is the K value to be equal to 2. And then I'm fitting it and predicting it. The accuracy which I got is around 0.7. So let's try giving K equal to 3 and check whether the accuracy increases or not. Now you can see that the value of accuracy has increased from 0.7 to 0.83 because in earlier case there was overfitting. So the test data points weren't classified correctly, though the trained data points was classified correctly. So when you try increasing the value of K, there is a possibility that the accuracy might increase or decrease. So you have to do a grid search or hyperparameter tuning to make sure the value of K which you are using fetches you a very good accuracy. Now I'm observing the boundaries for KNN. So when I plot the boundary for the KNN, this is the boundary which I got. That is, there are three classes in this data point. So basically, I'm taking iris as we saw already. There are three classes 0, 1, and 2. So the classification done here is pretty good. That is, the red points are perfectly classified as red. And in blue points, it's trying to classify all the points properly by getting into the green region. And there are some blue points which are not correctly classified. That's why we have a very that's why we have a 0.83 accuracy. That is, there are very few points which are not correctly classified, but we are okay with this accuracy because if we keep on increasing the value of K or decreasing the value of K, either underfitting or overfitting might take place. So that's about KNN and decision tree. If there are any doubts, please to ask. Is there any doubts on KNN or decision tree? Okay, if there is no doubts,
അവനെ വന്നിട്ടുണ്ട്.
okay. If there is no doubts, we'll end the session here. We'll meet in the next session. I think it's on next.
கொலாப் நோட்புக்ஸ் நாங்கள் மெயில் பண்ணிடுவோம்.
We'll mail all the collab notebooks which are used in the session as well as in the previous session if you hadn't got it. So that's for today. We'll meet you in the next class. Bye.
ஹலோ ஹலோ சரி ஓகே மேம் ஓகே. ஓகே ஓகே மேம்.